After the discovery of electrons, it became clear that atoms were not indivisible, as Dalton had proposed. But what exactly is inside an atom? How are positive and negative charges they are arranged? What keeps atoms stable? To answer these, scientists explored radiation phenomena and developed atomic models, each one refining our view of the atom. Let's journey through these key discoveries and models. Research goal. At Research Goal, you will find research-driven courses that offer real research skills, data analysis training, and publication support. And best of all, it is incredibly affordable, costing less than other platforms. Join Research Goal today for free. Check out the link in the description box. Discovery of X-rays and radioactivity. Let's talk about the contribution of Wilhelm Röntgen. In 1895, while experimenting with cathode ray tubes, Röntgen discovered a new kind of radiation that could pass through solid matter and cause fluorescence. Since its nature was unknown, he called it X-rays. X-rays, they were produced when high-speed electrons strike a dense metal target. They are not deflected by electric or magnetic fields. They possess high penetrating power, later identified as electromagnetic waves with very short wavelengths, approximately 0.1 nanometer. This discovery opened up new ways to probe the internal structure of matter. Now let's talk about the contribution of Henry Becquerel in 1896. Soon after, Becquerel found that certain elements emit radiation spontaneously. It's a phenomena he called radioactivity. This field was expanded by Marie Curie, Pierre Curie, Rutherford, and Soddy. 3 different types of emissions were identified. They are heavy, positively charged particle, later identified as helium nuclei. Beta rays, they are high-speed electrons. Gamma rays, neutral, highly penetrating electromagnetic radiation. These findings, they reveal the complex internal structure of atoms and set the stage for atomic models. Thomson's model of the atom, 1898. Building on the discovery of electron, J.J. Thomson proposed the first structured model of the atom. He mentioned the atom is a positively charged sphere of radius 10 to minus 10 meter. Electrons are embedded within like seeds in a watermelon, hence called the plum pudding model. Mass and charge are uniformly distributed. The atom is electrically neutral. The model explained neutrality but could not explain atomic stability or the results of later scattering experiments. Still, Thomson's work earned him the Nobel Prize in 1906. Then comes the Rutherford's alpha scattering experiment in 1909. To probe atomic structure, Ernest Rutherford performed an important experiment. He bombarded a thin gold foil with high-energy alpha particles. The foil was surrounded by zinc sulfide screen, which smashed when hit. What was expected from Thomson's model? Alpha particles would pass through with minor deflection. What was observed was most alpha particles passed through undeflected. Some were deflected at a small angles. A few, for example 1 in 20,000, they were deflected by almost 180 degrees. These results led Rutherford to propose a new atomic model. Rutherford's nuclear model of the atom. From his observations, Rutherford concluded 1. Atoms are mostly empty space. Positive charge is concentrated in a very small dense region called the nucleus. The nucleus is tiny compared to the atom size, like cricket ball in a 5-kilometer stadium. Some of the model features, they include the atom consists of a dense nucleus containing all the positive charge and most of the mass. Electrons, they orbit the nucleus in a circular path like planet around the sun. Electrostatic attraction hold the atom together. The model was a huge leap forward but didn't explain why electrons don't spiral into the nucleus. The puzzle was addressed later by Bohr. Millikan's oil drop experiment, 1909 to 1911. While Thomson had found the charge to mass ratio of the electron, the actual magnitude of the electron charge was unknown. Robert Millikan solved this by using a brilliant experimentation setup. The setup was consist of tiny oil droplets that were sprayed between 2 metal plates using an atomizer. Their fall was observed through a microscope with a micrometer eyepiece. X-rays ionized the air, causing droplet to pick up negative charges. By adjusting the electric field, Millikan could make a droplet 1 fall faster, it can fall slower, or stay suspended when gravity and electric force were balanced. Some of the key insights from this experimentation was that Millikan found that the charge on each droplet was always an integral multiple of a fundamental value, which is Q is equal to n multiplied by E, where n is 1, 2, 3, which is integral multiple of fundamental value. He confirmed that electric charge is quantized. Because of this, Millikan received the Nobel Prize in Physics in 1923. These three contributions, Thomson's model, Rutherford's experiment, and Millikan's charge determination, completely reshaped atomic theory. For your competitive exams, the experimental setup and observations, they are critically important. You should also study how each model improved upon the previous one. That is what we have covered already. And the key conceptual breakthroughs like the discovery of nucleus, quantization of charge, and the limitation of the early models. The question can come from any side. As the science progresses through evidence, experiment, and refinement, you need to also understand all these observations, the experiments, and what are those refinements. The journey to understand the atom is a perfect example for that. All right, let's complete our other topics in the next video.